Hello, Mathemaniacs. I'm the Math Edumacator, and today we're going to continue our discussion on set theory. Last time we explained how set theory gives us numbers. Today we're going to be talking about how set theory gives us operations. Alongside numbers, the concept of operations is one of the two pillars of arithmetic. Basically, we have numbers, and then we have things that we do to numbers, ways that we combine numbers to describe different situations. Now, set theory has its own operations, and that's the topic of this video. In set theory, operations are performed on sets. We use them to describe different combinations of sets, and like in arithmetic, where operations performed on numbers will give you another number, operations performed on sets will give you another set. So here, I've drawn the same two-set Venn diagram that we've seen before, but I've colored in a little bit. There's actually four regions we've created when making this diagram. We have this overlap here between set A and set B that I've drawn in green. We have this part of set A that doesn't include what's in set B, and I've drawn that in red. Likewise, I have this part of set B that doesn't include anything from set A. And then I have everything that's not in A or B. That's the outside here that I've drawn in purple. So we can use set theory operations to sort of describe these regions and even different combinations of these regions. Maybe we want this region, this blue region, and the purple region. Okay? Or maybe you want the purple and the green region. We could find different ways to describe those using set theory operations. And so we're going to introduce those operations for you now. Now, there are three important operations in set theory: complements, intersections, and unions. Most of the time when we think of operations, we mean binary operations. This is like having two different numbers that are connected by either a plus sign or a minus sign, and so forth. Our first set theory operation is not a binary operation. It's more like just notation. The complement of set A. And we write this as just A with a little apostrophe next to it. We might call this A prime or A complement. The complement of A is everything that is not in set A. So you see here, we have set A is the circle right here, and the part I've shaded is everything outside of it. So the whole universe except for set A. That's A complement. Belonging to the complement of a set means that you don't belong to that set. Suppose we talk about the set of all books. Any book I have is going to belong to the set of all books. If I were to talk about the complement of the set of all books, that would include everything that's not a book, like this tape, these pencils, this protractor, this hacky sack, this necktie, this bowling ball, this shoe. Now we have our first binary operation, intersection. The intersection of set A and set B. We write this using this little upside down U and putting it between our two sets. The order that you write these sets in doesn't matter. Yeah, I could have said B intersect A, and it would mean the same thing. The intersection of A and B includes everything that is both in set A and in set B. So this region here is the overlap that we've talked about. This is the intersection. Verbally, we describe the concept of intersection using the word and. You have to be a part of one set and the other set in order to be part of the intersection. Suppose that you're going to fix a spare tire. What are some of the things you need? Tools, a spare tire. It's a joke. Ask any topologist you know, they'll laugh. Now, if I only had the tools, or I only had the spare tire, I can't fix the flat. I have to have both of them. Both of them are required. Lastly, we have our second binary operation, union. The union of A and B, which we write with a right side up U in between our two sets A and B. Like intersection, the order that we write the sets in doesn't actually matter. I could write this as B union A, and it would still work. As long as an element belongs in A or B, that element belongs to the union. You only have to be in one. So the union of A and B includes all of this region. As long as it's in A or it's in B, it's in the union. Verbally, we describe the union of two sets using or. Now, in English, we use something that's called the exclusive or. Usually, if you hear someone say you can have brownies or you can have candy, they don't mean you can have both. You've got to have one, but not the other. However, in math, it's different. We are more inclusive. Set theory uses what's called the inclusive or. If we used set theory rules, then if I were to tell you could have brownies or candy, that means that you could have brownies, you could have candy, or you could have both. So now we come back to our original picture with the four regions. And what we're going to do is that we're going to try and describe these regions using the operations that we talked about so far, or different combinations of those operations. So before I show you, I want you to pause the video and then try and use different combinations of the operations we talked about to describe each of these different regions. So go ahead and do that now. Everyone ready? All right, let's go. Now, it is possible that the way you wrote your description may not look exactly like the way I'm going to write mine. That does not necessarily mean that your description is wrong, but there are some ways to check. So first off, the easiest one here probably is the green region. So this is in both A and in B. So it doesn't include anything that's by itself in one of the other sets. So this here is going to be the intersection of A and B, the green region. Next, I'm going to try to describe the purple region. This one is a little bit trickier, but if you think about it this way, if I were to take the union of A and B, that's going to be everything in these three regions. That's going to be the red, the green, and the blue. Now we already know that the purple is everything else, everything that's not in the red, green, and blue sections. So what we can do is we take A union B, and then we take the complement of that. So everything that's not in the union of A and B. So see, I wrote down A union B in parentheses, and then this to show that it's the complement of that. Now, the other two sections are a little bit harder, but we should be able to see that if I can figure out how to write the red section, then that will tell me how to write the blue section. We're going to look at it this way. If I wanted to depict set A includes the red section and the green section. Now, I only want the red section. So I have to figure out how I can get the red section while excluding the green. Well, we know how the green section is written. That's right here. So I need everything that is both in A, but not in A intersect B. So we're going to use another intersection. A intersected with the complement of A intersect B. So the complement of A intersect B would be everything that's not in the green region here. And if we intersect that with A, then that's going to include just this red section right here. Using the same logic, the blue region is everything that's in B, but not in the overlap between A and B. And so we want to have B intersected with the complement of A intersect B. So in order to be in the blue region, you've got to be in B, and you've got to not be in A intersect B. You've got to not be in green. Now, I briefly talked about disjoint sets in one of my other videos. So now we're going to look at that in the context of these operations. So if I have these sets A and B, what would be the intersection of these two sets? Well, there's nowhere where these two sets overlap. So it's impossible for something to be in both A and in B at the same time. So the set that we create when we take the intersection is the set of nothing, which we call the empty set. And I mentioned that in my cardinality video. We denote the empty set using a little circle with a bar slash through it. And this is what the intersection of A and B looks like if A and B are disjoint. Now we could also try to take the union of A and B, and that's where things get really interesting. So I'm going to take the union of these. Now let's think about numbers here for a minute, cardinalities. We've got 4 things in set A, these 4 dots here, and we've got 3 things in set B, these 3 dots here. What would happen if I tried to take the cardinality of the union? So now I just have to count every dot as long as it's either in A or in B. So that would be 1, 2, 3, 4, 5, 6, 7. So that's 7. However, we noted the cardinalities of A and B individually. So A had 4 and B had 3. Now we know that if I combine 4 and 3, I get 7. So I ended up with the same thing that I did here. Coincidence? The answer is, it isn't a coincidence. This is how we derive the operation of addition from set theory. We define our operation addition using our plus sign, such that the cardinality of A plus the cardinality of B equals the cardinality of the union of A and B when A and B are disjoint sets. So in other words, whenever we write this, what we really mean is this. We've come up with something new, which is actually familiar to us, that is defined in terms of these things we've established in set theory. Does this definition make sense? Well, disjoint sets are apart from each other. I have this collection over here of things, and this collection over here of things. Now, the union of those 2 collections is if I were to put both of these things into a new collection. So I get the stuff in my new collection by combining the number of things I had in the first one and the number of things I had in the second one. And that is exactly what addition does. What about the other operations? Well, in my video, there can be only one operation. I mentioned how every other arithmetic operation is ultimately derived from addition. So set theory gives us addition, and addition gives us everything else. And that wraps up this week's episode. We'll have more in store for you next week, so tune in.
If you enjoyed this week's video, please like and comment below and share the link. If you want to see more, subscribe to us at the Math Edumacator YouTube channel and follow us on Twitter at Math Edumacator.